We are now going to transition to radian measure versus degree measure of an angle. And to do that, we're going to have to discuss the arc length around a circle, and that's going to lead us into talking about angular speed. So we're going to get started by looking at the circle that goes around the coordinate plane within the coordinate plane. We've got the origin at 0, 0, and the radius is going to equal 1. We're going to come talk about that in a moment, but regardless of whether or not the radius is 1 or 5 or 1,000, we do know the measures around a circle. We start at 0 degrees, and then this first turn is going to be a 30-degree turn. Then we're going to have 45 degrees, 60 degrees, 90 degrees. So that's going to be our first quadrant. So these are critical points around the circle because that's going to allow us to make 30, 60, 90 degree angles and 40 triangles and 45, 45, 90 triangles. So we're going to turn 30 degrees, then 15 degrees. See, this is 30 degrees, then 15 degrees, then another 30 degrees. Another 15 degrees, and then another 30 degrees. So we go 30, 15, 15, 30. 30, 15, 15, 30. 30, 15, 15, 30. So 30 degrees, then 15 gives us 45, then another 15 gives us 60, and then 30 gives us 90. And we're going to do that now, continuing our turn all the way back to 0 degrees. So 90 degrees plus 30 is 120, plus 15 is 135, plus 15 is 150, plus 30 is 180 degrees. Once again, we're going to go into the third quadrant. 30 degrees later gives us 210, plus 15 is 225, plus 15 is 240, and plus 30 is 270 degrees. One last time, plus 30 degrees is 300 degrees, plus 15 is 315, plus 15 is 330, and plus 30 is 360 degrees. So our position at the positive x-axis is 0 degrees, and at the same time 360 degrees. So we start at 0, we end at 360. Now what this is going to allow us to do is it's going to allow us to create these angles. Let me show you real quick before I create the others. This is a 30-degree turn, so I have a 30-degree angle here. That's going to give me a 30, 60, 90 triangle, and I'm going to be able to do some pretty cool things with this triangle. Same thing with 45 degrees. Let's make that as straight as we can. Let's try one more time. There we go. And the same thing with 60 degrees. So you can see that my 30-degree angles are with blue ink. So 30 degrees away from the x-axis is blue ink. I don't really like that. Let's try that one more time. Blue. Yeah, I keep messing up, don't I? One more time. Third time's a charm. Oy. I think my dots aren't in the right spot. Yeah. Let's move the dot. Finally, right? There we go. Okay. And then the red. And then our green. And then you'll see the 45, 45, 90. And then you'll see the 60, 30, 90. So now that angle with the origin is 60 degrees, and then 30 degrees, and then 90. But still a 30, 60, 90. So we've got a couple of 30, 60, 90s, 45, 45, 90. And then this is kind of a neat thing. You've got this triangle. I'm going to use a highlighter to show you. This triangle right here is reflected across the y-axis. It can also be reflected over the x-axis. So here we'll do this one in green. See, it's reflected over the x-axis and reflected, oh, let's try that one again, reflected over the x-axis, just like that. So you've got the same triangle in quadrant 1 as you do in quadrant 2, 3, and 4. They all just have, you know, different x and y signs. So we'll talk about that more in detail in a little bit. But what I want to do is I want to let you know that knowing these angle measures is really important. So knowing that you have 0 degrees, 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and then finally finishing with 360 degrees. Being able to go around the circle like that fairly quickly, like I did, is going to help you. Knowing all of these new facts, as you know the multiplication facts, 7 times 5 is 35. You don't even have to think about it. Knowing these facts in that same manner is going to make a huge difference for you. It's going to help you get through a test a lot quicker. It's going to help you understand the next lesson a lot easier. Letting this build up and not really knowing what's being talked about is where students struggle. That's why they struggle in trigonometry. If there's a struggle, that's why. It's because we don't have the facts down from the previous lesson first before we learn the next lesson. So putting in that extra time makes a major difference. Now a radian, 1 radian, we shortcut radian with RAD, is equal to the measure of the central angle. Now the central angle is the angle that's made with the origin. So here's our central angle in quadrant 1. Okay. Here's our central angle in quadrant 2. Okay, there's our central angle in quadrant 2. We even have a central angle in quadrant 3. That's our central angle in quadrant 3. It's the measure of the central angle that intercepts an arc that we'll call S that is equal to or equal in length to the radius length. Now, 1 radian is exactly the measure of the central angle that intercepts an arc that is equal in length to the radius. So here's our radius, okay? Here's our radius. I'm going to make a circle out of this. Let's get a good circle. Okay, there's our circle. Now the radius is going to be, let me make that circle have a center. There. Yeah, that looks good. That looks good. That looks good. Okay, so now here's a radius, right? That's a radius. Now, I'm going to draw another radius. I'm going to draw a radius over here. Okay? Any radius in the circle is equal in length to any other radius in the circle, because all the radii in the same circle have the same length. What they're saying is one radian is equal to the measure of the central angle that intercepts an arc that is equal in length to the radius length. So let me show you. We've got an arc, okay? So this arc has a length. If I were to take steps from this initial point to the end point, if I were to walk along that arc, how long would it be? How long would that walk be? If I were to walk along the radius, how long would that walk be? When the walks are the same length, that's when you have exactly 1 radian measure of an angle. Okay, I'm going to get rid of all this other stuff that's messing up our picture now. It doesn't belong. Okay, could that red length be the same as the blue length? Or is this orange length equal to the blue length? No, the orange length is most definitely a longer walk. It is a longer length than the blue length, right? Much longer. I would say that if I were comparing the two, I think the red length might be equal to that blue length. It's very, very close. And that is where 1 radian of a measure of an angle is going to be. So we might say that this is, now this isn't really 45 degrees. I kind of moved this, right? So 45 is right there. 30 is going to be right about there. 60 is going to be right about there. So I would say this is about maybe 65-ish degrees, maybe 65-ish, maybe 70-ish degrees. I mean, it's definitely a rough sketch, but that looks like it might equal about that length. I'm not sure how many degrees it is, but I do know that rather than writing 65-ish degrees or 70 degrees or whatever the measure of the degrees is, I know that this is 1 radian. And what makes this 1 radian is the fact that the arc length equals the length of the radius. That's 1 radian. Now, what happens if I take this arc length and I double it? What happens if I double it? What if it's 2 radian lengths? 2 radian lengths. That means that this angle right here would be 2 radians. So rather than saying 120 some odd degrees, we could say 2 radians. 2 radians. Do you see? It was difficult for me to say 120 some odd degrees, but it wasn't difficult for me to say 2 radians. And if I did 3 arc lengths, so it's 3 arc lengths that measure 3 radius lengths. 3 arc lengths, 1, 2, 3, that measure the same length as 3 radius lengths would measure. That would be 3 radians. That's radian measure. So let me show you here in a nice clean circle. We're going to have a radius right there. We're going to call that R. This arc length that the angle in standard position measures, standard position, starts at the positive x-axis, rotates counterclockwise. That is 1 radian, 1 radian measure. So theta is equal to, now theta is now going to always be measured in radians. So theta is the measure of the central angle in radians, not in degrees, in radians. And it's equal to a fraction. The arc of the whole circle, I think I need another C in there, the arc of the whole circle divided by the radius, which is equal to 2 pi r over r. That's 2 pi. Now that is once around the entire circle. So the measure of the central angle that goes all the way around the circle, would be an arc length of 2 pi r, that's the circumference of an entire circle, divided by the radius length. So that would be the measure all the way around the circle, not in degrees, but in radians. So all the way around the circle is 2 pi radians. So once around the circle equals 2 pi radians. What's once around the circle in degrees? 360 degrees. Much easier. 2 pi radians versus 360 degrees. Now we have a formula. What if we don't go all the way around the circle? What if we only go partially around the circle? Well, then theta is going to equal the arc length divided by the radius length, which is equal to S for your radius, for your arc length, over R, your radius length. And this, once again, measure in radians. Measure in radians. So now that we know once around the circle is 2 pi, let's practice. So we have 0 radians. So now we're in radian measure. Radian measure. 0 radians all the way around is going to be 2 pi radians. So we start at 0 radians and then we turn all the way around the circle and we get 2 pi radians. What if we go halfway around the circle? Well, halfway around the circle would be 2 pi divided by 2, which is 1 pi. And what if we took that 1 pi and divided it in half? That would be pi over 2. So we'd have 1 pi over 2. Here, let me show you. 1 pi over 2. 2 pi over 2. 2 pi over 2 is pi. 3 pi over 2. 4 pi over 2. 4 pi over 2 is 2 pi. Let's do that again. 1 pi over 2. 2 pi over 2 is 1 pi. 3 pi over 2. 4 pi over 2 is 2 pi. So now let's write that down. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. 4 pi over 2 is 2 pi. We can take our circle and we can cut it up into, let's do the parts in the middle. Let's cut up our quadrants into halves. So that means I'd have 1, 2, 3, 4, 5, 6, 7, 8. I'd have 8 pieces of the pie. Actually, 8 pieces of 2 pi. That's kind of funny, isn't it? Okay, 8 pieces of 2 pi. So 8 pieces of 2 pi. 8 pieces of 2 pi is 1 pi over 4. So listen to me. This was, I'm going to do this very lightly here. I'm going to do this very lightly. There we go. I'm going to look because I just don't want it to, there, that's very lightly. and that's very lightly. But now you can see it. So we have 0, and then 1 pi over 4, and then 2 pi over 4, which is pi over 2, and then 3 pi over 4, and then 4 pi over 4, which is pi, and then 5 pi over 4, and then 6 pi over 4, which is 3 pi over 2, and then 7 pi over 4, and then 8 pi over 4, which is 2 pi. Now we can break our circle up into 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces. We can take 2 pi and we can break it up into 12 pieces, which is pi over 6. So we're looking at the gold. The gold and the gold. Let's make that the gold. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got 1 pi over 6, 2 pi over 6, which is pi over 3. 3 pi over 6, which is pi over 2. 4 pi over 6, which is 2 pi over 3. 5 pi over 6, 6 pi over 6, which is pi. 7 pi over 6, 8 pi over 6, which is 4 pi over 3. 9 pi over 6, which is 3 pi over 2. 10 pi over 6, which is 5 pi over 3. And 11 pi over 6. And one more, 12 pi over 6. 12 pi over 6 is 2 pi. Now, pi over 6, pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Those are all my pi over 6s. None of those reduced. My pi over 3 came from 2 pi over 6. 2 pi over 3, that was a reduced number. 4 pi over 3, that was a reduced number. And 5 pi over 3, those are all my pi over 3s. Those were all reduced numbers. Notice where all the green ones are. Notice where all my pi over 6s are. They're all 30 degrees away from the x-axis. And all my pi over 3s, 1 pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Those are all 30 degrees away from the y-axis. Pi over 4s are all in the middle of each quadrant, which is 45 degrees away from either axis. And then I have the quadrantal angles, pi over 2, pi, 3 pi over 2, and 0 or 2 pi. This is very important for you to be able to reproduce just like you do multiplication tables. So these are things that you want to have memorized. So we start at 0 radians, pi over 6, pi over 4, pi over 3, pi over 2. If you need to press pause, you can press pause, but you're going to want to go as fast as I'm going with practice. So you're going to want to memorize this. 2 pi over 3, 3 pi over 4, 5 pi over 6, pi. 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, 11 pi over 6, and 2 pi. Now another way that you can do this that might help you go through this a little bit faster is by coordinating your effort so you're not having to remember or slow up. Start with your quadrantal axes. 0, 2 pi, pi over 2, pi, 3 pi over 2. Then go to your pi over 6s. 1 pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Then go to your pi over 4s. Pi over 4, 1 pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And then your pi over 3s. 1 pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. That might help you memorize easier that your pi over 3s are going to be closest to your y-axis. Your pi over 6s are going to be closest to your x-axis. And your pi over 4s are going to be smack dab in the middle of each quadrant. So that's the beginning of radians. We're going to talk about coterminal angles with radians. We're going to convert radians to degrees and degrees to radians so we can go back and forth. And we're going to compute angular speed using radians.